Okay, so hopefully you can hear and see me again. I don't know what happened, but we lost our internet connection for about 30 seconds or a minute. And then my broadcasting software went all cuckoo. So hopefully now you're seeing and hearing me again. I think that my stream is back. But I'm going to have to go back a step. So hopefully you got everything up to the LED is fully tested, the display part. Now we need to go handle the counters. And I forgot as I was doing that step 8 is, okay, thank goodness. I forgot that step 8 is the red LED part of the display, and that's supposed to tell us when something is negative. So what I did is I went up to line 85 and I started to put it to 127 and I was thinking I'm ready to start counting, but no, I actually want to see if I can make the red light come on when R6 is a negative value. So I just made it -1. I'm not going to worry about what that does to the display. I just want to know, does -1 make the red LED come on? And then I will change that to 1 and hopefully the red LED won't come on, and then we'll see what happens. So I set on line 85 R6 to -1 to work on the red LED part. It tells me here, by the way, that the red LED is tied to B6. So when R6 is negative, B6 needs to come on. So I'm going to use a comparison for this. I'm going to compare R6 with 0, and then what I need to go do is see, no, you can't see any of that code. Sorry, I'm all thrown off now. So one more time, I went to line 85. I started the counter at -1 for this part of the software. Didn't change anything about the display. Now I'm here on part 8. So what happens is if R6 is less than 0, the red LED tied to B6 should come on. I remember, by the way, that the Bs are in R5, so because I was just working on B LEDs, so Bs are in R5. But what I need to know is what's the condition that tells me that one value was less than another. Since we're talking about positive and negative type values, this is signed. Okay, so now we go, this is where I dropped a second ago. I turned on the browser and I started to try to load homework 9, because homework 9 has a link to conditional branches and conditional branch instructions and condition codes. So let me see, I think it's the condition codes one that's the most adjustable. Let's see. No, I don't like that one. Let's try conditional branch instructions number 5. Yeah, this is the one that I want. So what I'm looking for is signed less than. So I'm going to look through the uses here for signed ones. That's unsigned, unsigned, signed. Overflow, I don't care about that. Signed, overflow, I don't care about that. Unsigned, unsigned, signed. Greater than or equal to, nope. Signed less than, that's what I want. That is bacon, lettuce, and tomato, but it's the LT part that I'm interested in. I want signed less than, which is LT. So that's where I am getting that from, is these codes that tell me the outcomes of comparisons. Okay, so let me hide the browser again. LT. So I can use this if-then construct to look for the conditions that I'm interested in. So this is called an if-then instruction, which kind of feels funny, but this is saying basically if the prior comparison yielded it was less than as a result. So if R6 is less than 0, and the less than is for signed, which means it can be negative. So if R6 is less than 0, it definitely is negative. And if that's true, look how I changed the condition. So this time I want to OR something on that less than outcome. It feels funny at first, and the homework is meant to address why this is this way, but we'll talk about that when I get past the circuit. Anyway, so if the comparison was less than, then I'm going to OR on that less than outcome. It's just the way that it works. So I'm ORing R5. That's where the B stuff is, and I want to do B6. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So I don't care about these first three. This is 2 to the 4th, 2 to the 5th, 2 to the 6th. So the B pins are tied to R5. That's where the value is. So I'm going to OR in that one, 4, 0, which should cause the red LED to turn on. Remember, I hard-coded R6 to be negative. So the display is going to do whatever it does for -1, but I want to see if the red LED is flashing on and off because, hey, negative value, negative value. So I'm going to go back and do this process again. Assemble / compile. Elf. Bin. Flash. Jolly good. So I'm going to press the black button. And the red LED is coming on, and that's a good sign because I have a negative value in R6. I'm going to go quickly change that. And by the way, I just happen to know from having practiced this, -1 makes all the bits come on. So I'm going to change this to 1. And what should happen is the red light will no longer flash, and only the first LED should come on to show me that R6 has just that 1 bit in it. Okay, so I'm going to go change the counter only this time for this part of the test. So for me, it's line 85. I'm going to make R6 be a +1. And then I'm going to go recompile it and all that stuff. What should happen now is the red LED no longer comes on because this is a positive value. And then the display should show me what 1 looks like as 8-bit binary. So clear, assemble, elf, bin, flash, jolly good, black button. And now the red LED is not flashing on. And the reason why just that 1 LED is flashing on is because it's displaying the counter value, which is 1, and then they all turn off, and displays it again, 1, they all turn off. So because 1 is not negative, the red light is not coming on, and that's what I wanted. Okay. So where are we? We need to do... There's a part 9 and a part 10. All right, well, we'll just do it. Pretty easy to do. Yeah, okay. So you get to see a new thing here as well. So now I am going to set up to either count R6 up or count R6 down. And the way I know which direction to move R6 is based on what R7 is. So when R7 is 0, I'm going down. When R7 is 1, I'm going up. All right, so we're going to do something slightly different here because instead of just an if-then, an if, we're going to use an if-else. So if-then-else. And the way you set these up is the condition that you're looking for. So in this case, if R7 equals 0, I'm going to do one thing, which is subtract from it. So subtract when it's equal 1 from R7. But because of this E part, this if then else, I can actually attach another conditional instruction with the other outcome associated with it. So I'm going to subtract on equal, but I'm going to add on not equal, which is what the E part lets me do, which is super, super cool. So if R7 is equal to 0, I'm going to subtract 1 from R6. That's the counter. If R7 is not equal to 0, the only other thing it can be is 1. So I'm going to add 1 to R6 instead. So look how beautiful that is as assembly language. These are conditional instructions. There's a homework question which we'll try to get to today. But you can set up sort of trees of decisions in ARM. So this is an if-else. If it's equal, subtract. If it's not equal, add. It looks funny, but that's the logic of it. That's number 9. So that's fairly straightforward in terms of the logic. If R7 is 0, I'm going down, subtracting 1 each time. If R7 is not 0, the only other thing I'm going to allow it to be is 1, which means we're going up. That's number 9. That's kind of useless without number 10, which is to turn it around. So the whole idea is if R6 is on negative 128, I need to switch the direction that I'm moving. If R6 is on 127, I need to switch the direction. So it's telling me to use test equal, and that's really just so that you have tried it. So I want to see if R6, ooh yeah, this is going to be a fun one. Use test equal. Well, we'll just, so anyway, we're checking the counter now. When the counter touches negative 128, then we need to change the direction of R7, the direction indicator, to go up. I'm just going to do it this way. So if it is equal to 128, then I need to change R7 to be 1. That goes up now. So I'm going to test R6 to see if it's negative 128. If it's equal to 128, then I'm going to move on that equal condition. I'm going to make R7, the direction indicator, be 1, which means go up now. That affects this code we wrote on number 9 a second ago. If R7 is 0, we're going down. If R7 is 1, we're going up. And I know to change R7 to go up when it hits 128, but I also need to, I'm just going to do it this way. If it's 127, then I need to make R7 be 0, that's going down. So R7 can only be 0 or 1. 1 means go up here. Add. 0 means go down, which is subtract up here. Okay, there's that. The last step here, I don't know what's going on with the internet. I hope that it's working. It seems a little laggy. But hopefully you're getting something. The last thing is to go to line 85. I'm going to refresh my display because something don't look right. Okay. Last thing is to go to line 85 and do what it told me to do originally, which is make it 127. So what should happen now, it's going to start at 127. It's going to be in counting down mode. So it's going to clear the display, all of it. It's going to clear the A part of the display. So all this means is every time it comes back through, it's going to refresh the display to nothing and then turn on the LEDs that match the parts of the 8-bit output we want to show. We have a little delay just to make the circuit easier to follow with your eyes, basically. Then we turn on we enable the parts of our 8-bit display that show us the value that R6 currently is. So the first thing we'll see is R6 at 127. It'll go 126, 125, all the way down to 0. Then it will become -1. The red light should now be part of the display, and it will count down until it hits -128. And then it will turn around and start counting its way back up until it's 127. So we got to be patient here to see all that work. So every time it goes through this display logic, it's going to check to see whether or not the current value is a -1, and if it is, the red light comes on. It's going to take us a while to see that part. Then it's going to either count up if we're in going up mode, or count down if we're in going down mode. Then it checks as one final thing to see if we need to reverse direction. So when we bottom out at -128, we start going back up from there. And when we top out at 127, then we change directions and start going down again. So clear. So now I'm going to go build all that stuff. Assemble. Oops. Line 184 has a mistake in it. It does not like that -128 there. So we're going to have to do something about that. It does not like my -128. Okay, so it's complaining about line 184. So when that happens, you get some kind of error about a fix-up and constants and stuff. Sometimes, and this is what we're going to try, sometimes that's simply a matter, we'll try it, of putting a register in between the value and the test. So I'm just going to pick a register that doesn't matter, like R9. I'm going to put 128 in there, and then I'm going to test R6 and R9. So if you get errors about values, sometimes it can help to put a middleman register in the mix. So let's see if that helps. Okay, so that did help. I just put a middleman in there. I knew from experience that sometimes with a hard-coded value, it did not work to test equal R6 against -128. So I just offloaded that value into another register and then did a test equal between two registers, and that seems to have made it happy. Assemble elf bin flash. Jolly good. I'm going to press the button. It's going to be showing 127 and then 126. So we won't see the red light come on for a while, but we'll watch it sort of count down. 127, 126, 125, 124. I'm not going to count them all. But what you'll see happen is the lights will kind of move down toward 1 and then 0, and then a different pattern will start to display. And we'll know we're closing in on 0 because these high-end bits will sort of go off. So it's working its way down. If you were to write these out in binary, it would likely be true. That's 2 to the 7th still, which is 64. So we'll just wait patiently. I guess we could have gone from like 10 to -10 and proved the point. All right, so notice now it's working its way down. I'm just going to patiently wait it out. It's going to take a little while. Oh wait, this is 2 to the 5th, so we're not that far up there, right? 2 to the 5th isn't that huge a number. But anyway, we'll sort of drink it in. Now is a good time while we're waiting for my circuit to execute to ask a question in chat or request that I highlight a different piece of code if you're not seeing what you want. I'm going to tilt this up. So there's my little 8-bit display working its way down slowly. It just hit 15, by the way. Okay, we're getting down toward single digits. Here we go. We're about to hit 1. 3, 2, 1, 0, nothing. Negative. 1, negative 2, negative 3, negative 4, negative 5. I'm going to let this keep running, but if you watch it, it's running slow enough where some values. So this is Tues complement that you're seeing right here. In Tues complement, this bit right here is always going to be on. So did you notice for the positive values, this 2 to the 7th bit was never on because in Tues complement that would never be used for an 8-bit number. So we are right now counting down toward negative 127. Sorry, negative 128. Negative 128 will be this one piece by itself. Is that true? Something like that. And then it's going to turn around and come back up. Okay, so that took me a little bit longer than I wanted to, and also we had the hitch with I lost my internet. So I'm going to end up having to post 2 videos, like a part 1 and a part 2 from today, since I had to stop the stream. So if you're using YouTube, just be on the lookout. There'll be 2 videos for today, but I'll put in the title part 1 and 2. So anyway, that's what that does. What we're seeing is the binary view of the value in R6 plus the red light indicating whether or not the value in R6 is negative or not. So when the red light's on, that means it's a negative value. Okay, so I'm going to go a little bit quicker through homework. Hopefully that hiccups with the streaming didn't mess anybody up too bad. But just let me know in chat if I moved on too quickly for you. I'm going to move over to the homework 10 questions and kind of quickly just go through the answers. Homework 10 is mostly just an orientation thing to ARM. So it's just kind of more, we're using an ARM processor, and why shouldn't you know a little bit about ARM processors since we are programming them. So homework 10. Okay, so it turns out that the ARM family of processors actually has 3 different instruction sets. There's what we sort of call the full ARM instruction set, and then we also have thumb instruction set and thumb 2. So the full-on ARM instruction set are 32-bit instructions. Which isn't really, it's just, that's just is what it is. Do ARM instructions provide access to, yes, ARM instructions can be conditionally executed. Which I sort of hinted at that the other day, or maybe in the last homework, I think. So when we say ARM instructions, we mean 32-bit instructions. So, oh, sorry. Yeah, I forgot to re-enable the browser. Sorry about that. So ARM instructions are 32 bits. All ARM instructions can be conditionally executed. Now, we just wrote some instructions that are conditionally executed, so sort of pay attention for what's coming here in just a second. the main thing about an instruction being 32 bits or another size is that more bits means that they require more space to store them when they're in an executable file. So 32 bits per instruction for full ARM instructions, but they can all be conditionally executed, which makes life wonderful for the assembly programmer. You may not feel like that's true right now, but the code that we just wrote with the if-thens all over the place is a lot nicer than what you do in Intel assembly. A lot nicer. Okay, so the next question, thumb. So thumb is a variant in the ARM processor world of instructions. Thumb instructions are 16-bit. So they are smaller. And that has obvious advantages, at least I think. Is that you get the code size is smaller. So thumb instructions are good for very, very small spaces, like very small systems with tiny amounts of memory in them. This is why ARM has created that variant of their instructions, is so that you can cram your instructions into a very small space. And that's the main advantage. Disadvantages. Thumb has very few conditional instructions, which means that the assembly programmer doesn't have the convenience of those really cool if-then and if-then-else constructs. You have to write a lot more code, basically, to do logic. So conditional instructions, wonderful, but Thumb doesn't have very many of them, and the reason it doesn't is because it's trading smaller size for and giving up more convenience. It's also true, by the way, that Thumb instructions are slower to execute generally. But Thumb is usually used in very small systems. So we're not talking about like laptops and phones and stuff. Tiny embedded sensor systems and things. Okay. Thumb 2. Thumb 2 is a mix of 16 and 32-bit instructions. You can sort of imagine what Thumb 2 is trying to do is find a balance of the better performance of 32-bit, the convenience of conditional instructions, and the density of the Thumb set. So Thumb 2 is sort of trying to take the best of both of those worlds and put them in one place. So it's a mix of 16 and 32-bit instructions with the intent of balancing having the performance and conditional execution that you get with a 32-bit ARM set and the code density that you get with the 16-bit Thumb set. None of that super matters for our work. It's just you're in a class that uses ARM processors, so why not know? But the reason why I ask is because I'm heading into this question where, well, our processor, which is an ARM v7, what are its instructions? thumb and thumb 2. So our processor does not have the full ARM instruction set, but it does do thumb 2, which is how we're able to do things like conditional execution that we were doing in lab 10 and we'll also do in lab 11. I don't know why I put only, it doesn't really matter. So thumb and thumb 2. Oh wait, no, yeah, only. I do need only because part of the question was ARM. Thumb and thumb 2 only. So our processor is that thumb, basically it's the thumb 2 instruction set that is sort of a balancing act between performance and conditional execution, convenience of 32-bit ARM instructions, and code density of thumb instructions. Doesn't really matter because we're just going to write the assembly that we write, but if this is a thing that you're into, now you know. Okay. I'm going to start copying some of my answers to speed myself up a little bit. So this question about the TST instruction, we just used it a whole bunch. Allows you to test if individual bits are set or not. So if you're checking I'll give it, yeah, I'll do an example. So the answer is actually these first two parts. So the test instruction allows you to check to see if one or more bits is either set or not set. That's it. The actual sort of math or logic that it performs internally is an AND instruction. But just as an example, if you wanted to see if a bit is set, then you do a test on a bit and then you look for a not equal result. That tells you the bit was set. If you look for, let's just test the net bit. That would tell you that 0x, that bit was not set. So you can actually use the test instruction to see if bits are set or not set. For us, it's almost always, in our code, we're going to be interested in seeing if bits are set because we're going to make our circuit respond to that. So those are just examples. You don't have to prove to me that you're a great typist by getting the examples, i.e. you're just sort of mindlessly typing the things you see on the screen. These are the answer. The description of the TST instruction is that it allows you to test if bits are set or not set. And then a college level answer would also include the detail that the internal operation is ANDing the two operands. These bits down here, these pieces down here are just showing you that you can write assembly code to test set or not set. Okay, so write the ARM instruction to test if bit 2. So bit 2, remember, is the 2 squared bit. So that nibble, that's the 2 squared bit. So we would do a test. Upper or lower doesn't really matter. Register R0, and then the bit pattern would be 0x4. That's how you'd write the test instruction to test that specific bit. And then technically you would follow that up with a not equal, and then do something else with that result. Okay, the test equal instruction. So this just tests for equivalency. The basic answer is it allows you to test whether or not two operands are equal. You can also use the CMP instruction for this, but you'll see me use test equal because it Sometimes it's just easier for me to see in code, to be honest. It allows you to test if its two operands are equal. The college answer would include the fact that it actually runs exclusive OR on the two operands. In practical terms, that usually is not going to matter to us what the internal operation is, but the college answer would include that detail, so I did. Okay, write the ARM instruction to test if R0 and R1 are equivalent. R1, and then you typically follow it up with an if-then and then some conditional instruction. Technically, it's just that one instruction, but it's almost always going to be followed, so that would mean yes, they are equivalent. I'm running a little long, but we're on the last two, so let's just get it over with. Okay, so number 9 is a three-parter. The IT instruction, we just did a whole bunch of it. It means if-then. But let's just answer the three pieces. So question part 1, what does IT do? So the IT, that instruction allows you, allows the conditional execution up to 4 subsequent instructions. So in today's code, we used it to execute up to 2 with an ITE, but you'll see in time that you can actually do ITTT, like if do 3 things, and you can also do like ITTE, if do 2 things, and then an else part. You'll see all these constructs, but in Thumb 2, the way you set up to do sort of if, then, else in assembly is with this IT instruction. And it actually allows you to chain together as many as 4 subsequent instructions conditionally. It's a cool thing. And it doesn't take very much practice, I think, to get used to it. I know you're not used to it yet, but you will get used to it. So that's what it does. Part 2 asks, what is the term used to describe instructions affected? So if you read the documentation, you'll see that when you chain instructions together after an IT, ARM calls that an IT block. I think that's useful to know because it's kind of like setting up a block in C++ with curly braces. So you use IT to set up a block of conditional instructions. I'm having to switch the screens. Okay. Part 3. What happens when the condition code provided as an argument to IT evaluates to true? If the condition code evaluates to true, then the next instruction is executed. We did a whole bunch of those today. So that's the answer. I'll also insert an example. So we did, for example, compare R6 and 127, and then we set up an IT block. And we set up an IT block with a condition code equal. So what we're saying is I want to set up a block so that if that comparison resulted in an equal, I do something. Now you'll notice what we did is we did a move when they're equal. So the conditional instruction has the same condition code attached to it. This means move if equal, but that thing right there is an IT block. And what we did is we moved 0 to R7. So that is an IT block. If this condition code is satisfied, then this instruction is executed. If this condition code is not satisfied, then this instruction will not execute. So that's an example of that. Number 10, write the instructions to test if R1 and R0 and R1 are equal. Okay. I'm switching between upper and lowercase instructions. When I'm coding, I usually do lowercase. Sometimes in my examples, I do uppercase just to try to make it readable. So we want to see if R0 and R1 are equal. Create an if-then block based on what them being equal. And then add 1 to R1 if that evaluates to true. So notice that the conditional instruction has the same condition code on it. So this is my if-then block. I'm adding 1 to R1. That's my if-then block. Notice the condition code is the same. So that's the three pieces that answer that question. Okay, so I'm going to sit here quietly. It was a pretty long session. Thanks for your patience through my weird internet outage. I don't know what that was about. Maybe the government doesn't consider the internet to be essential. I don't know. At least not for those few minutes in my house. Let's hope they don't do that. Anyway, so I'll wait for your questions. Otherwise, this is what we're up to. I'm going to add a note at the top. Just to remind you that Wednesday mornings, I'm online at 10 a.m. for question and answer, kind of like office hours. So we just did homework 10. We just finished lab 10, and then lab 11, we're going to at least start it on Thursday. We'll see how far we get. So we accomplished our goals today, even though we had to go long to do it. And then we'll see how far we get on Thursday. Thanks, you too. Sorry about the glitches. Thanks for your patience through that. Hopefully I have 2 pieces of streamed video, and I'll label them part 1 of 2, part 2 of 2, so that you can keep up with it. Thanks, Brooksy. So I'll be here on Wednesday morning for open Q&A, but if not, then I'll see everybody on Thursday at 8:30 a.m. and we will start working on lab 11 and see how far we get.